morning we have Tamunonye Cheetham-West telling us about finite quotients of fiber cusped three-manifold groups.
Thank you so much. I want to start by saying thank you to the organizers of the thematic program and the conference in particular. I'm not happy I wasn't able to be there in person, but yeah, I attended some of the mini course last week and yeah, learned things. Thank you all so much for such a great time. So I'm going to be talking about questions about like profinite rigidity for three manifolds. Almost always, in fact, all groups inside are going to be finite generated. And the other thing I want to like, please feel free to interrupt with questions as you have them. So we heard Eli's talk earlier in the day, so an hour ago, yeah. And so I will repeat things. And also there have been earlier talks on profinite rigidity. So some things we will see again. But like the objective, the goal towards which we're working this morning is trying to sort of like motivate this theorem. Like all four punctured sphere bundles over S1 are distinguished by the profinite completions of their fundamental group. So yeah, four punctured sphere bundles look like this. And hyperbolic is important. I need the property hyperbolic. And so here's an example, or a rather famous example, the magic manifold. It's a corollary of this theorem is that it is distinguished by its finite quotients among all three manifold groups. Okay, and so
are they distinguished among all three manifold groups, or just other four punctured sphere bundles?
All three manifold groups. So we've seen many times this definition of residual finiteness. It's a geometric group theory conference. I mean, what can we do? So a group is residually finite if every non-trivial element has non-trivial image in some finite quotient. And a residually finite group, or an infinite residually finite group, is going to have lots of finite quotients. In particular, Nathan told us last week this theorem of Hempel, building on the geometrization theorem that tells us that when you take the fundamental group of a compact manifold, you have this group is residually finite. And so in particular, like you will have for your three manifold, you will have lots of finite sheeted covers. You can make them regular and so on. Towers as high as you, and much of the discussions last week on this, I mean, thinking about these towers of covers, trying to, for example, think about like this like log torsion volume formula, thinking about towers for different reasons. And but I'm thinking of a different tower. I'm thinking in this case of like I don't call it a tower, more like the standard term is like a system of finite quotients. And all you need for that to remember that is the first isomorphism theorem for groups. Right? If you have a smaller finite index subgroup, you have a map, a bigger finite quotient, and you have maps onto smaller finite quotients. And that forms like an inverse system. And this inverse system has an inverse limit. And that inverse limit is the profinite completion. And an equivalent reformulation of residual finiteness is that a group embeds inside its profinite completion canonically. Okay, and so we have one of the remarks that was made last week was about this effective recognition for three manifolds. Right? If you are given three manifolds, sort of like you meet them in the wild, and you try to say, how can I tell if these two are different? Or, you know, one way you can do so is to consider them up to some finite sheeted covers. You can think of like and algorithms for these are very fast, you know, to say, oh, give me all the order 10 finite quotients of this particular group. You know, and and when you look at those lists, and you know, and you see that those lists are different, you know that you have different fundamental group, and you know that you have different manifolds. Okay. But the reverse question is like, what can you say about M and N when the finite quotients, respectively, when the profinite completion is the same? And these are like the same questions that we have already seen in the earlier talk by Liu. So here's like the first thing to ask is like, can this happen? Can we ever have like three manifolds whose fundamental groups have the same finite quotients? And the answer to that question is yes, and in different ways. But the way I'm going to talk about today is I'm not going. This is like manifolds with a solved geometry. Manifolds with solved geometry. So these are unsolved torus bundles. So this is T2 cross I, and I am gluing the gluing map for the first one is this matrix over here in GL. Is that a question I hear?
No.
Okay. So the gluing map for the first one is this matrix in GL2, and the gluing map for the second is this matrix. And an observation made by Funer is that even though the fundamental groups of these mapping tori are different, their profinite completions are the same. And the reason for that is that these two are an example of what are called STB pairs. They are non-conjugate in GL2, but they have conjugate images in GL2 Z mod M for all M bigger than 1. And so while the fundamental group is an extension of Z2, so you have Z2 here, and you have Z on this side, Z squared rather. This is Z squared, please. Okay, and the profinite completion is going to be an extension as well. It's going to be an extension of, in this case, there's going to be a Z squared hat. Okay, and this is going to be a Z hat. All right. And then these non-conjugate monodromies, A and B, upon completion are going to become conjugate in the outer automorphism group of Z squared hat. And so that is going to make the extensions be isomorphic. And so as is implicit in the title, I'm considering today fibered three manifolds. And so I'm always thinking today of things of the form like sigma cross I, where you're gluing by some monodromy. I'm thinking about hyperbolic things. And so the surface, if you want to see, I'm going to use to glue is in a pseudo and not of isotopic class. Okay. Any questions at this point? Thoughts?
So far, so good.
Okay. So we've seen earlier, right? That the profinite completion detects certain properties of the three manifold. So, for example, we've seen like the first homology is quickly detected, and all that you need to know to prove this is that when you have all the same finite quotients, you have all the same abelian quotients, and there's like the abelianization satisfies a certain universal property, and so one can see that the homology, they are abstractly isomorphic. But right now we even know much stronger things because of work of Liu. And then we know that when M fibers over S1, N fibers over S1, when they have the same finite quotients as originally due to Huygens appearing, and in a stronger way to Liu. There's also the detection of hyperbolicity by Wilton-Zaleski, and this we think of like as a profinite analog of the geometrization theorem. It says that pi1m M is hyperbolic if and only if pi1m hat has no non-peripheral Z squared hat. And then in one of the early detection results, Wello-Friedl proof for knots and Brighton-Reed proof for all three manifolds, that the complement of the figure 8 knot is determined by its finite quotients among all three manifold groups. So it's a conjecture that when you have a finite volume hyperbolic three manifold, the profinite completion determines the manifold. It's like Liu was saying, like this is like a kind of like think of it as a profinite monster of rigidity, right? And not just among all three manifolds, but even among all residually finite groups. And it's a very strong conjecture. What evidence, I think, do we have for it? We have examples, right? We have examples due to Brightson, McReynolds, Reed, and Spittler. We have examples, further examples due to Brightson, Reed, and I also have some examples building on work of Brightson, Reed, and Brightson, McReynolds, Reed, Spittler. Of lattices in PSL2C that are completely determined among all. This is like the absolute profinite rigidity results. So for example, you mentioned the Weeks manifold, and then there's like this lattice PSL2C adjoint omega, PSL2O3 that Bianchi observed. All right. The second evidence I want for this conjecture, at least you can think of a subcase where I replace among all residually finite groups with like all three manifold groups, right? The strong evidence for this conjecture is Gardam, Giles Gardam, like went into the SNAPPy census and compared everything in the SNAPPy census against things in the other things in finite census, and was able to distinguish all of them by finite quotients. And the SNAPPy, that's a lot of manifolds. That's a lot of manifolds. And the third very strong evidence is in the work of Liu. Liu proves that there are at most finitely many finite volume hyperbolic three manifolds with the same fixed profinite completion. And as has been said, as he said earlier, right, anytime you have two finite volume hyperbolic manifolds with the same finite quotients, those manifolds are going to have isomorphic Thurston norm balls. But very remarkably, apart from the fact that the Thurston norm balls are the same and the fiber classes are lined up, in the closed case, your corresponding pseudo-Anosov monodromies will have the same stretch factor. They will have the same number of periodic points by index. They will have the same unstable, they will have the same, number of singularities, K pronged for K at most 3, and they will have the same orientability status. The stable and unstable solutions will have the same orientability status. And so that's like the strongest evidence that number one, like those pseudo-anosovs should be conjugate in the mapping class group of the surface. Those manifolds should be the same. Like we don't have any examples of two pseudo-anosovs with the same. I do not, what I should say is I do not know of any examples of pairs of pseudo-anosovs of a fixed closed finite closed surface with all the same Liu data that are non-conjugate. Any questions at this point?
That's great.
Okay, so we've also heard mentioned, right, all once punctured torus bundles, this result of Brightson, Reed, Wilton, are distinguished by the profinite completions of their fundamental group. And I want to talk a bit about this result because it's sort of like it's building on this result that's like the main theorem is proved, combined a lot with work of Liu. right? And so what's the idea for of that Bryson-Reed-Wilton use? In particular, they use two properties of the mapping class group. So this is like mapping, not just mapping of out F2, where of course F2 is like the fundamental group of the once punctured torus. That out F2 has the congruence subgroup property, and that should give people pause. But let me allay those fears. So it does not have the congruence subgroup property with respect to z squared. Okay, like that's like a historical fact, but it does have congruence subgroup property with respect to F2, to the free group, right? And what that means is that when you define a characteristic subgroup of a finite index characteristic subgroup of your surface group, and you consider this map, the induced map from out of F2 to out of pi1 mod k as a principal congruence quotient, then every finite quotient of out F2 is a congruence quotient. So it's a theorem of Asada that's like out F2 has the congruence subgroup property. And like this, there's like an older question of Ivanov, but asking this for just more general surfaces, and point people like to like probably like the work of Atom Kent, the work of Ben McReynolds, and so on. Right, and so not only is CSP used, the other thing is like out F2 is omnipotent, and this like due to Wise and Bryson-Wilton. And what omnipotence means is that we can prescribe orders of images in finite quotients for independent families of infinite order elements. That's a mouthful. So if you have a family of elements, or let's do a simple family. You have sort of like gamma 1, gamma 2 in out F2, and you know that no power of gamma 1 is conjugate to a power of gamma 2. So that's what it means to be independent. Then you can prescribe orders of images and finite quotients. You can say, you know, I want this image to, I want this to be divisible by 13, and I want that to be divisible by 15 for gamma 1 and also for gamma 2. And these end up being useful. So I give like a proof sketch, right? Like when you start out with a once punctured torus bundle, say with monodromy A in the hyperbolic case, so A is going to be the pseudo-anosov of the once punctured torus, right? Then you start out like with you have an extension of this form, like a discrete extension, and you promote that to a profinite extension. And then Bryson-Reed-Wilton, they argue that any manifold with the same finite quotients as a once punctured torus bundle must itself be a once punctured torus bundle, say with monodromy B, right? And then, crucially, this ability to prescribe orders in characteristic quotients. And if you remember from the solved manifold example, it is this action on characteristic quotients that describes what the structure of the profinite extension is. And so having congruence subgroup property and having omnipotence helps you see that A and B cannot be independent. That in particular, A must be conjugate to B or to B inverse. In fact, A and B have to be conjugate in GL2. Are we good at this point? Questions, thoughts?
People seem to be good.
Okay. I think I'm moving a bit too fast. Huh? Okay, anyway, so theorem. So we're looking at the theorem today, like all hyperbolic four-punctured S2 bundles over S1 are distinguished by the profinite confusions of the pi1. What's like the strategy? You start out with like a 3-manifold, right? Which is like a hyperbolic four-punctured S2 bundle over S1. And you use Wilton-Zaleski to see that any manifold with the same finite quotients as your manifold of choice has to be hyperbolic and has to be cusped. And then by theorem of Liu, your cusped manifold will fiber. So this is like Liu's paper, like the almost determined paper in Invenciones. You fiber over a surface with the same Euler characteristic as the four-punctured sphere. And then the next thing to see is that like it actually has to be that this surface has to be the four-punctured sphere. And so N fibers over four-punctured S with some monodromy as well. And so in particular, then you now use specific properties of the mapping class group of the four-punctured sphere. In particular, the fact that it also has congruent subgroup property and is omnipotent to see that the two monodromies have to be conjugate. And so M has to be the same as N. So that's like the rough sketch. And so the fact that like the mapping class groups of like N punctured spheres has CSP, this is like a theorem of Donaghy Habata. And they are also proved, I think, by Mick Reynolds, Ellenberg, Mick Reynolds, the Thurston's proof, I think. And then for omnipotence, like this comes from the fact that like this is virtually free. This is virtually free, and Brightson and Wilton prove that virtually free groups are omnipotent, right? And so I have a lot of time, and so let me talk about the ideas for A, right? So in particular, so A, right? When we know that we have this correspondence of surfaces, so sigma sort of like Gn, sorry, the Euler characteristic chi of sigma Gn is the same as that of the four-punctured sphere, then we know that it's sort of like 2 minus 2g minus n is going to be equal to 2 minus 0 minus 4, which is minus 2, right? And so there's an ambiguity there. Like this could be sigma 0, 4, or it could be the twice punctured torus. So let me write that in the, this could be a sigma 1, 2, right? And then, well, so our goal then is to show that sigma Gn has 4 punctures. And if we're able to do this, we win. Okay? And so the idea for showing that this is a 4-punctured surface is that we observe, for example, so let's see, a warm-up case, right? If M has a monodromy, so I'm still doing A. If M has a monodromy phi in the pure mapping class group of sigmas 0, 4, then in particular, then N fibers over the 4-punctured sphere. And the reason for that is like the cusp counting. So let me, this is I should call this a claim, right? And the proof of this claim is that M is 4 cusp. And then by Wilton Zaleski, or more specifically by Chagas Zaleski, N has to be 4 cusp as well. And a 4 cusp hyperbolic manifold cannot like fiber over a twice punctured torus. Okay. twice punctured. So that's like the case when M is pure, when M has pure monodromy. When M does not have pure monodromy, then we can sort of like do a count, and the count is sort of observing. So what did I call the monodromy on the last page? Okay, yeah, I called it P is not in P mod sigma 04. Well, we observe that pi1m sits in the following extension. We have sort of like a 1 pi1 sigma 04 pi1m z1, and this monodromy is acting sort of like the induced map on fundamental group up to inner automorphisms is by the action over here of by the action over here of like a stable conjugation action by a stable letter. All right. And so we can observe then that for appropriate power, say k factorial, the number of cusps, in particular 4, is going to be the number of fixed conjugacy classes in pi1 sigma 04 of the t to the k factorial action. And in particular, it's going to be more, so this is, I think, but moreover, when you take completions, like this is going to be the same as the number of fixed conjugacy classes in pi1 hat sigma 04 of the t to the k factorial action. And this is at the level of the profinite extension. Okay. Are there any questions at this point? Or questions on Zoom?
I have a question that's maybe not very local to the spot in the talk. So if you'd rather have it later, then that's fine.
Oh, go, Dave. I need a pause.
Okay. It sounds like your argument is not using the fact that 4 punctured sphere bundles are commensurable to punctured torus bundles, and they're commensurable with like very small degree covers. So I'm wondering if that's useful at all.
No, I don't use that here. No. Right. All I'm trying to do is count the number of punctures, and once I can do that, I can say, oh yeah, this fiber is over the same surface. Yeah, and so thank you for that. Yeah, and so in particular, we have the following for n. This is like a theorem of Lie. We have the following picture of extensions. 1 to, let me see. So you have pi1 sigma 04 to, sorry, let me make that better. We have a pi1m, have z1. And then you have the profinite diagram, the profinite picture in here. pi1m hat to z hat to 1. And all you've done is sort of like just complete it, right? And so now, when you choose your isomorphism, okay, to fix the isomorphism phi between pi1m hat and pi1n hat, you're going to get a sort of like an analogous sort of like profinite extension. pi1, let me call this, yeah, pi1 sigma gn hat to, and so here I have a phi I have a pi1 n hat to z hat to 1. And last of all, but not the least, let me see. On this side, what Liu proves is that when you do a multiplication by a profinite unit, say, so this is like a times mu in z hat star. When you change your profinite monoidromy by multiplication by mu, you're going to get a discrete vibration over here. By 1 n to z to 1. Right? And so now, if you want, so the upshot is that if one can argue that this is the same as the surface, then all you're doing is comparing the monodromies. And I'm going to give this monodromy a name right now. I think I'm going to call it psi. Right? And so, in particular, the number of fixed conjugacy classes of, in this case, I'll just call it phi of t to the k prime, which is also going to be a stable letter acting on that, right? Will be the same. Let me write them. Will also be 4. And this is a more general statement than I think I'm letting, so that in particular, we do not only detect the Euler characteristic, we also, I think, detect the topological type of the fiber in the punctured case. And so we can, and thus we can do comparison of the monodromies, say, psi and phi in the mapping class group. And our old friends, having CSP and omnipotence, lets us see that phi has to be conjugate to psi plus minus. And the only way that can happen is like for the bundles to actually be the same. Okay. So there are questions that arise, of course, naturally. So questions I have till I run out of time. So number one is sort of like omnipotence for mod sigma 0 n. I mean, in this case, I'm talking for n at least 4. Right? How does one approach this kind of question? Number two, and the reason I'm saying this is that this is like a general framework that one is letting on for kind of proving, because let me make a philosophical aside, if I may. Like, for trying to show that like three manifolds, hyperbolic three manifolds, are determined by their profinite completions, one can use Eagle's virtual fibering theorem to pass to a common corresponding fibered cover. And so if you can resolve the question for fibered things, then you will just be considering commensurable things. In particular, what one has proven is that if one can resolve the profinite rigidity for fibered three manifolds, and what all one is arguing is that, distinguish every three manifold in a particular commensurability class from everything else in the commensurability class, right? So that's why, in particular, I care about like fibered things, and I'm sure that's also why others do. Right, so omnipotence for mod sigma 0 n, then much harder, right? Congruent subgroup property, problem for mod sigma 0n. So again, like there have been the approaches by using algebraic geometry. So that's like the work of sort of like Diaz, Sonagi, Abeda. The more work of Autumn Kent uses more explicit sort of like mapping class group stuff, and also some things done by Marco Borgi, right? Congruence. So, but in many cases, like especially also like in the closed case, the congruence subgroup problem is still open. And then the third thing is like this question regarding the Liu data of pseudo anosov, right? Pseudo anosovs in, so I'm thinking of a mapping class group of a surface of appropriate complexity determined by their number one stretch factor, number two number of periodic points by index, number three transverse orientability of stable and unstable foliations, and number four number of 3 or more pronged singularities of stable and unstable foliations. I think that the answer to this question should be yes. Like it feels, yeah, it's too close for. I mean, they should be conjugate. So when I say pseudo anosovs, I mean conjugates. I actually mean conjugacy classes. So where do I write that? Let me put it here. Up to conjugacy. So I think with these 3 questions, I'm okay to stop. Thank you so much for listening. Thank you for your time.
Question.
Hi, I have a question about your question 3. So the number of periodic points by index. So by index, you mean like just the period of the periodic points, or?
No, the Lefschetz fixed point index of the appropriate power. And
is that something that's like, you can, if I give you like a train track map or something, is that something you can, that sort of can be summarized like in a finite amount of data? Like pseudo-anosovs, can I compute some, I don't know, probably some like L function or something that I can check these things are the same or different, or like?
I do not know. I do not know.
So I sort of have a 2-part question. Am I correct that CSP for the genus 2 mapping class group is known? And if so, how far can you get in that case? And also, what does omnipotence look like for closed surfaces?
So
3-part question, sorry. Yeah.
Oh yeah, thank you. Is that Nick?
Yeah.
Hi, Nick.
Hi, Tam.
So genus 2 with, I think genus 2 with 1 puncture. Yeah, I don't know about closed. So CSP, I think there's CSP for genus 2 with 1 puncture. Gaugy only works, I think, that far.
I see.
I don't know about omnipotence for genus 2 with 1 puncture, the mapping class group.
I also have a question about question 3. Hi, Tam, this is Dave. So is the point of, is the relevance of this question to profinite things that this is all information that Lou can see from the profinite completion?
Yes, and also Liu is here.
In some sense.
Yeah. So Liu can read off this data from sort of like from the correspondence from a profinite. So after using sort of like work of Friedel, Kim, Friedel, Vidusi to say that, oh yeah, that's a fiber class, I can recognize testing one. Lee goes further to say that I can recognize stretch factor, can recognize these periodic points, like some character theory it does to say that, oh, I actually recognize this Lechette's fixed points. And in fact, it's from the fixed points that he gets the stretch factor. It's of like, there's like that Lim-Soup power formula.
If you could get a yes answer to this third question, how close would that be to just, pinning down the manifold from its profinite completion?
So a yes answer to this question it implies profinite rigidity among three manifolds for all fibered things, for all fibered hyperbolic things. And somebody with more knowledge should check me on that. But that's what I think. Yeah, I think that if the answer to this question is yes, then all fibered things by work of Lee have to be completely determined among three manifolds. I mean, I'm talking, please, always in this for this one, like in the closed case.
All right, so let's thank Tam again. We're back at 11:30.